What you're looking at here is a classic optimization problem. So optimization, just kind of listen to the word optimization. You're looking to try to find either, depending upon the problem, the largest or the smallest amount of something. The largest being finding the max, the smallest meaning finding the min. And so essentially these are word problems that need you to apply a first derivative test to them. This version of it right here, this is a classic area perimeter setup. So they really like to bring this relationship in a bunch. Ideally, what you want to do on these is start by drawing out a picture of your scenario. So this one is saying that we want to fence in a rectangular garden. There are usually going to be some standard, geometry shapes. Here specifically, though, we're going to use our house for one side of the garden. So my picture, if I was drawing it, might look something like this. So there's part of it, and then the house is over here, so I don't need to know that side of it. Well, from there, I go ahead and I label my side. So this makes sense to label X since it's running left and right, and this side I would call Y and Y. When you're doing these problems, you're generally going to have what's known as a constraint equation, something that is limited, and then you're usually then from there going to have the thing that you want to maximize, the equation that you're trying to find, you're trying to optimize. This one we're trying to maximize it because we're trying to find the largest possible area. The constraint on this problem is coming in from the amount of fencing that we have. So that amount of fencing, that's going to be a perimeter. So our perimeter right now is limited to being 32 feet. We also can come up with an equation for what the perimeter would be. So our perimeter based upon this model is it would be, we've got 2 y's, and then plus a single x. That's the equation for the perimeter. And so what we can now do is just set those two things equal to each other. We know that whatever the perimeter is has to equal 32. So 32 has to equal 2y plus x. Now you need an equation that you're trying to optimize, an equation you're trying to find the max of. And so on this one, we are trying to find the max area, and we are trying to find the max area of a rectangle. So look for all those key words to help you find the equations you need to use. So we're looking for the area of a rectangle formula. So the area of a rectangle is base times height, length times width. So for this model, I would say my base is x and my height is y. Ideally, what we want to be able to do is run a first derivative test on that equation right there. But we're not able to do that until we get this equation talking one variable. So this thing either needs to talk all x's or all y's. That is where your constraint comes in. So we're going to take our constraint equation over here, and you're going to solve it for x or y. It really doesn't matter. In this scenario, it's easier for me to get x by itself, so I'm just going to do that. So I minus the 2y over. I get 32 minus 2y equals x. Now that I know what x is equal to, I can take it and shove it into this area formula. So I get the area equals 32 minus 2y, that's what x is, and then times y. Now I'm ready to go. From here, I can run a first derivative test, a first d test, because I've got an equation that's talking just one variable. So we start running our standard first derivative process. Step one of the first derivative test is find the first derivative. I always tell people derivatives are like a burning house. You do not rush straight into that. You need to stop and kind of look at it for a moment. When I go to take this derivative right now, I could take it as it looks, but I have two things being multiplied, which means I would have to run a product rule. And if I don't have to run a product rule, I don't want to run a product rule. And so my first move is actually going to be to distribute that y value into both pieces. I know how to multiply stuff real easy, real quick. So this becomes 32y minus 2y squared. So there's our original equation. And now we're ready to take the derivative. No product rule required. So we just have to follow our power rule. There's that unwritten one right there. We bring that down. That gets us 32, and then subtracting 1 from the power gets us y to the 0, and anything to the 0 power, no matter what it is always 1. So 1 times 32, and then we bring the 2 down, we get 2 times negative 2 gets us negative 4y. So step 1 of our first derivative process complete. On to step 2. Step 2, we need to find critical values. Critical values occur in 2 places. They occur when our derivative equals 0. That's the one everyone remembers. They also occur when our derivative is undefined. And you really just want to look out for that undefined situation whenever you've got fractions and you have an x on the bottom there, because that could give you want to look out for when you would have division by 0. Also, if you have endpoints, then you would want to plug those endpoints in. We don't have endpoints, we don't have fractions, so we just get to use the straightforward set the derivative equal to 0 to find your critical value. So I set that equal to 0. It's a pretty straightforward little algebra problem. We want to get y by itself. I'm going to go ahead and add the 4y over to the other side. Make things positive whenever possible. Life lessons from math. From there, I would go ahead and divide by 4, just trying to get that y by itself. And we end up with y equals 8. This is all you know right now is that this is a critical value. So the kicker on this is you get to that point and you can feel pretty confident that that's going to be where your max is happening at. However, we don't know if that critical value is actually at a min right now or if what we're looking at is a max. And so we cannot stop our standard first derivative process. We need to go do that first derivative test, that number line game, to determine if our critical value is actually a max or if it's a min. So same game here, draw out our number line. We're going to mark our critical value, which is 8. And then from there, we are going to choose test values on either side of it. So choose something to the left. I'm going to choose 1. Something to the right, I am going to choose 10. And then from there, this is a first derivative test. And so we are plugging everything into our first derivative. So we would do a prime of 1, and we would do a prime of 10. So plugging 1 into that, I get 32 minus 4, which is going to get us 28. So we get out of there a positive value. Remember, we don't really care about the number. We just care if it's positive or negative. So a positive derivative tells me the graph is headed up and increasing. Plugging in 10 into that situation, you're going to end up getting out of there negative 8. And so don't care about the number. Just care that that is negative and therefore decreasing. And so because our graph goes increasing to decreasing, we can also see the shape here, right? If we just sort of draw ourselves a little sketch, we can see that what we did find was the max. And so now we have one portion of our answer. But go back and see what they want out of you. So step 4 now is to kind of answer the full question. They want to know what the dimensions are. Dimensions means your length and your width, or your base and your height. Well, we know what one of them is. We know that y is 8 feet. And then technically you've got an equation that you created right here with your constraint that you can plug a y value into and figure out what x is. So then our x value is going to equal 32 minus 2 times that 8, that y value. And so from there, we are going to get out that x is 32 minus 16, which is going to get us 16, and then that's feet. So that's our x direction, that's our base. There's our y direction, that's our height. So the dimensions are 8 feet by 16 feet. And then this one asks the additional question of what is the actual area? Well, we know that our area is x times y, our base times height. That's where we started. And so now we know what the x is. The x is 16. We know what the y is. The y is 8. 16 times 8 gets us 128, and we're talking area, so this is now feet squared. You know, whenever you're doing optimization problems, just be super careful about your units. They always want to know what they are. But optimization problems, the method here really is you've got to find a constraint equation, Find an optimization equation. Really, the optimization equation is what you want the most because it's what you have to take your derivative of. Usually a picture can help you. Oftentimes these are standard geometry shapes that they want you to have area and perimeter formulas memorized for. So make sure you know all your standard geometric shapes. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.